All right, let's talk about something that's literally all around us, making our modern world possible, but that we almost never think about. We're going to do a deep dive into the unsung hero of engineering, getting rid of heat. It is the hidden force behind pretty much all of our technology. So let me start with a question for you. What could a nuclear submarine deep under the ocean, the laptop you might be watching this on, and the International Space Station orbiting a couple hundred miles above our heads, what could they possibly have in common? I mean, they're from completely different worlds, right? But they all share one fundamental and kind of surprising engineering challenge. And the answer is waste heat. Yeah. Every time we generate power or process information or, just make something move, heat is the inevitable leftover. And this isn't some design flaw, it's just a basic law of physics. So the real challenge, the puzzle that engineers have to solve over and over again, is how to move all that heat from where it's being made to somewhere it can be safely let go. So how do we solve this universal problem? Well, the first and most fundamental tool in the engineer's toolkit is something called the heat exchanger. Let's break down exactly how this core piece of tech actually works. Okay, so a heat exchanger's main job is pretty simple. Move thermal energy from a hot fluid, and that can be a liquid or a gas, to a cooler one. But, and this is the absolute key, the two fluids never actually touch. The perfect example is your car's radiator. You've got hot engine coolant flowing through all these little tubes, and then cooler air gets blasted past the outside of them. The heat moves right through the metal, cooling the liquid down, but the air and the coolant stay completely separate. Now, believe it or not, a simple change in direction can have a massive impact on how well these things work. In what's called parallel flow, the hot and cold fluids are traveling in the same direction. You get this big initial burst of heat transfer right at the beginning, but then it fizzles out pretty quick. But in counterflow, the fluids move in opposite directions. This simple tweak keeps the temperature difference between them way more consistent along the entire length of the exchanger, which makes it dramatically more efficient at moving that heat. Okay, so we've got the basic idea down. Now let's scale it up, like way, way up. When you're talking about massive power plants, oil refineries, and huge chemical processes, you need something that's standardized, powerful, and unbelievably reliable. So let me introduce you to the king of industrial heat exchange, the shell and tube. Just try to imagine the sheer complexity of a modern refinery. You can't just go and design a totally new custom cooling system for every single one of the hundreds of processes going on. It would be a nightmare. You need a system that's tough, that's well understood, and that you can set up in a million different ways to meet specific needs. And that demand for a reliable, scalable solution is what really pushed the industry to standardize. And the solution they came up with was the TEMA standard. The best way to think about it is like the ultimate Lego kit for engineers. Seriously, the Tubular Exchanger Manufacturers Association created this amazing modular system where you can pick a standard shell, that's the big outer can, and then you can mix and match different head pieces for the front and back to route the fluids exactly where they need to go. It lets engineers build the perfect exchanger for almost any industrial job. Super fast. And this modular system also helps solve some really common, really big problems. For instance, when you heat up hundreds of long metal tubes, they expand. And if they're bolted down at both ends, that stress can literally tear the whole thing apart. So the U-tube bundle is a really clever fix. By just bending the tubes back on themselves in a U-shape, the whole bundle can freely expand and contract inside the shell, safely dealing with all that thermal stress. Of course, the real world is messy. Over time, all this unwanted gunk in the process fluids, we're talking minerals, rust, even biological stuff, it builds up on the heat transfer surfaces. They call this fouling, and it's a huge problem because it basically creates an insulating blanket that just chokes off the heat transfer. So engineers have to plan for this. They actually have to over-design the exchangers from the start, knowing that their performance is going to get worse and worse over time as that fouling layer builds up. So shell and tube exchangers are the big, powerful workhorses of industry, no doubt. But what if you need to move a ton of heat, really, really fast, over a distance, and with zero moving parts? For that, we turn to a technology that honestly feels a little bit like magic, the heat pipe. To really get your head around how different this is, just think about a solid rod of copper, one of the best thermal conductors we have. If you heat up one end, that energy just slowly creeps to the other end. A heat pipe, though, it's not a bridge, it's a heat superhighway. It doesn't just passively conduct heat, it actively moves it from one place to another using the physics of phase change. And the numbers are just staggering. The effective thermal conductivity of a sodium heat pipe can get up to 100 million watts per meter Kelvin. Just to put that into perspective for you, solid copper is about 400. That's not just a little better, it's a completely different class of technology. It's literally the difference between walking somewhere and teleporting there. So, how does this magic actually work? Well, it's this beautiful, self-contained four-step cycle. First, heat comes in one end and boils a special working fluid, turning it into vapor. Second, the pressure from that vapor blasts it at nearly the speed of sound to the colder end of the pipe. Third, the vapor hits the cold end and condenses back into a liquid. And when it does that, it releases all the stored energy it was carrying. And fourth, a wick structure inside the pipe uses capillary action, kind of like how a paper towel sucks up water, to passively draw the liquid right back to the hot end to start the whole cycle over again. No punks, no moving parts, just pure physics doing all the work. So we have this incredibly powerful way to move heat around. What happens when we take that exact same principle and we shrink it way, way down to solve the problems of our modern microelectronics? And this is where it all comes full circle. The exact same physics that engineers use to handle the extreme temperatures on satellites and spacecraft are now being miniaturized to cool the super powerful processors in our laptops, our game consoles, and our smartphones. This has led to the development of the micro heat pipe. And when I say micro, I mean it. We're talking about diameters smaller than a single human hair. At this tiny scale, you don't even need a separate wick. Instead, they're designed with these sharp-angled internal corners that use the liquid's own surface tension to create the capillary flow that pulls heat away from those intense little hotspots on a computer chip. It's brilliant. Okay, so we've gone from these giant industrial plants all the way down to microscopic pipes. So what's the big takeaway here? Why does all of this thermal engineering really matter in the grand scheme of things? At the end of the day, this isn't just about making things faster or stopping them from melting down. It's about efficiency. Every single bit of that waste heat is a byproduct of energy being used. So if we can manage it more effectively, it means we waste less energy. And that has these profound global implications for sustainability and power consumption. This technology really is the invisible backbone holding up our modern world. It's what allows the massive data centers that run the cloud to even exist. And it's absolutely essential for the safe and efficient operation of everything from nuclear reactors to geothermal power stations. And at the exact same time, it's what allows the impossibly powerful and tiny devices we all carry around in our pockets to even work. The entire trend of smaller, faster, more powerful electronics, all of it depends on our ability to solve this one fundamental problem of heat. Which really leaves us with one last fascinating question to think about. We are constantly pushing the limits, cramming more and more power into smaller and smaller spaces. This battle against waste heat is only going to get more intense. So as we look to the future, you have to wonder, what's next? What will the next great heat mover be? What new innovation is out there that's going to unlock the next generation of technology?